Okay, this video is about the vertical axis wind turbine that goes on the roof, not yet manufactured. And the previous video was about the whole house fan, and there wasn't anything on the blades on that video because it wasn't on the drawing. And to save a drawing and open another drawing, when you don't know how to edit and combine these little bits and pieces, I have to let it sort of run continuous. So we're going to stick some of that in here. This is cross sections of a fan blade from what we call the root to the tip. You see they get smaller as they go out. Also, the angle that they meet the air at changes because this one close to the hub is turning a lot less feet per minute than one that's swinging out at the tip. The tip of the blade turns much faster. Let's take a look right here. Well, that shows you there's 3 blades, but that doesn't show you much anything else. Well, crap. I don't know where it is. It's on this page. Must be really tiny. Well, we're not going to fool around with this anymore. I'll just have to explain what it does. You have one blade. We're going to call it the red blade, but I can't tell from this drawing which it is. Wait a minute. Oh, that didn't work. Okay, we're back to this, explaining it. Red blade goes straight through from one side to the other. It's completely flat in the center. The blue blade passes underneath of it. So the blades are at the same elevation. They ride one behind each other. But the hub goes down underneath of the red one and back up to the other side. Purple does the opposite. The blades, again, are running the same plane as the red one. But its hub, it goes up, over top of the red, back down into the other blade. The blades are one piece from side to side. The actual hub has 12 holes. I don't know how many's on that one. This is a proof of concept. And the actual, the drawing of the actual blades, which is same cross section and same hub and everything, but the ends tilt up at like winglets. It saves some air being thrown off the sides that take horsepower but don't do anything for you. And there's probably not a picture of those hubs crossing. Of course not. Make it too easy. This is 6-inch spacings of what the blades look clear across. Let's get on to the turbine. We'll have to do better than I'm doing on this. Okay. A little smaller. Okay. This thing's 6 feet in diameter side to side. And it's got these 4x8 sheets of plywood standing on end. And what this is for, say the air was coming from the bottom of the screen going up. As it comes up, wings make lift by what's called angle of attack. If the front of the wing is higher than the trailing edge, get it closer. If the front of the wing here, if the air is coming straight across, you be coming from here going across that. This wing will be pulling up. This one is pulling up. That one's pulling up. This one is from about 4 to 5 degrees lower than straight up. Low, if we call that the chord, from the center of this airfoil tip to the back, there's an imaginary line. That's the chord line. And when that chord line goes positive, it's always lift. But because of the shapes of airfoils, if it's down as much as 5 degrees, it's lower coefficient of lift, but there is still lift. Normally that the first one in the diagram here wouldn't be making much lift, but it'd be in the ballpark. But these fixed baffles here, that's like an air booster. It's collecting air from the edge of this panel here to the edge of that panel there, which is a lot wider space than the 6-foot rotor. Okay, so but the trick to it is every bit of air that comes in is going down this side of the thing, trying to turn it the direction that the wings are trying to pull it. Air that would have come down the other side and pushed against the back sides of these blades, the top of the airfoil, would have been trying to turn it the wrong way. So you're losing power by any air that goes down there and tries to reverse the rotation. That's what's wrong with the Savalius types of wind generators. I don't care how fancy you make them and twist you make them. If it has to fight the oncoming air and you get the difference between the two, you're just not making any real power. It has to be a monstrous, huge thing. That's why the horizontal axis, like you see along the highway with the big blades turning fairly slow, actually the tips of those things are going really fast, but they're so huge they look like they're turning slow. That's why they do the kind they do, is because all the air that hits a blade is trying to turn it the correct way. There's no blade coming back into the wind like there is. This has blades that would have been coming back into the wind were it not for these boosters. I saw an advertising thing for the California Energy Commission about a federal grant. They built a turbine where this piece, they had just two baffles, but they turn around to stay facing the wind. It's a movable piece. The only times these move is if you have a, well, we call them hurricanes. What do you call them here? Typhoon. If you have a typhoon coming in, you think that you're going to get a bunch of tree branches and all kinds of stuff sailing across your stuff and breaking your blades. These are hooked together at the tip, and you just grab hold of any one of them, and it closes off and just puts the rotor in the box. You can also do that with a screw, jack screw, and a stepper motor, like the CNC machine moves the tool bits that way. But you could have that where when it hit a certain wind speed, it would close up itself, and then you'd have to manually open it again, tell it to go open. But it would just close and then shut off. Wind turbines have a term called cut-in speed. Normally the generator, which would be on this shaft underneath the turbine out of the weather, they would have all the coils run to ground when they're sitting still. When you turn them, they don't generate any electricity because they're run to ground. They also don't make any electrical drag because they're run to ground. So what happens is this thing, when it starts to build up speed as the wind turns it, you're reading the voltage across the coils that are run to ground. And when it hits a certain voltage, they call that cut-in voltage. So if it's a 3-phase generator, say you have a cut-in voltage that when it hits 29 volts, it ungrounds those things and starts generating electricity on that phase. So every third stator coil would be come on, and you get 1/3 of your output, and that would slow it down because you're taking power out. But if the wind is really picking up and it just sails right through that and goes to the cut-in voltage, which may be 2 or 3 volts higher for the second phase, it would turn on, and another 3 volts the third one would turn on, and it would turn on and off phases just to keep the speed above the cut-in speed. You're going to want as many of them on as you can keep turning. And after they're all on, and you get higher wind velocities, then the voltage goes up almost like a square of the wind speed. It's not really linear. It picks up really fast after a certain point. Let's see, cut-in speed. There's more to it than that, but that's the gist of how it works. Anyway, turn them on, turn them off. That puts more or less load on it, and you keep it up. And it's making AC power because you have these coils are in groups of 3, just like a 3-phase motor, and it's much simpler than the drive in the motor circuit. It's still going positive current and negative current. It's an AC current, AC 3-phase. It's about as efficient as you can use your materials. And to turn it into usable power that you can store, charge batteries, or put it in inverters to make 220 volt 60 cycle out of whatever kind of AC you're making and whatever voltage you're making. You generally make these things for like 48 volts or 24 volts. And then you use the inverter, which is just a bunch of big capacitors. You charge the capacitor up and then discharge it, and by by time, the time constant, and then you can get any kind of voltage you want. If it's a 500 volt capacitor, it would eventually go to that, even though you're only wanting to make 220. I'm sitting under a ceiling fan right now. It's a 3-phase fan hooked into a 220 single-phase line, and like all 3-phase motors, it won't turn on its own to start because you've only got basically 2 phases balancing each other, and it just sits there and hums, or it keeps drawing more and more power until smoke comes out. But what they do is they put a capacitor across the third leg. There's 2 ways to do it. One uses 2 capacitors, one uses 1. One capacitor, it will continue, once you turn it, it'll continue to run. Does that make sense? No, the motor itself will do its own commutation once it's turning. What the capacitor does is gives it the kick to start, gives it turn 1/3 of a turn. And if you want to be sure which direction it turns when you turn it on, you use 2 capacitors across 2 of the legs. A lot of times they call that start capacitor and run capacitor, but you can design a motor that only needs 1 that always turns the correct direction. Those are generally designed as reversible motors. You have a switch to make it run the other direction, but it's the timing on the capacitor ensures that it only goes the correct direction. This ceiling fan has a 1.5 microfarad 500 volt capacitor in it. It's a Westinghouse. They're 6 years old, run every day, except for the capacitors. The voltage in the Philippines runs up and down. I think it stays on 60 cycle pretty reliable, but as far as the actual voltage across the line, we'll see everywhere from 178 to about 260, 270. And that capacitor is balanced by, I don't know, 5 or 6 unknowns in an equation to get the exact size it needs to be for the inductance on the whole system. So that's hard on capacitors. And we were changing capacitors sometimes twice in a year. Can't buy them in the Philippines, had to bring them from the States. We could get 470 volt and 400 volt. We could get any kind of microfarads, like ours is 1.5s, but we could get one close and 470 volts. And sometimes it works and sometimes it burns the motor up. The one over the dining room table was rewound twice already because we were trying to use the wrong size capacitors in it and burn it up. So I could keep a jar full of them now. But we went to run them only on the highest speed. We don't ever run them on the first 4 speeds, only on the 5th speed. Or the first 3, it's 4 speed. First 3 speeds we never use. And because I had people pulling the wrong string, one for the light and one for the fan, and still burning the things up, I shortened the strings for the that runs the motor to where Filipinos can't reach them. It takes a ladder to get to it now. And we have not lost a capacitor or a fan motor since I shortened the strings. So I think that I'm right that don't run them on the slow speeds unless your line voltage is conditioned. If you have a box that, like an inverter that conditions it. Anyway, this is the, I don't know if I can get this thing to, it's just not going to cooperate. It'd be nice to see a 3D view of this. I don't know what I just surrounded, but I just got rid of a bunch of 700 pieces of something. They're so small that there are no seams. Now I can't find a picture. Son of a gun. Well, I bet this is boring. I smell the dislikes coming now if anybody ever comments. See, the thing is, nobody watches our videos, so I might be irritating somebody, but it's probably nobody's ever watched this video. Oh, they haven't yet because I haven't got it uploaded. But they won't watch it anyway. Why does it even show it to me if it doesn't want to make it big enough to see? Chasing you now. I hear the fan running on the computer. It's not liking what I'm doing here. What we're trying to do is find out a little bit of stray text or whatever that's on this screen. If I could run across the thing that was trying to center up, then we could erase it. Crap. I'm going to try to pause this. Wait a minute. Would you believe it only took about another 3 seconds to get this actually on the screen? Okay. Now, this is our blades. You can see that they're fairly long compared to the diameter. And this is just the curves that were used to generate these. They're just laying there, have never been erased. The axle that goes through this, it's connected on both ends to, it's a hub that you buy for a replacement for front of a car. The cheapest ones I could find were $6.70. They're before anti-lock brake models for a Dodge and Plymouth Caravan. They have a nice bolt pattern to them. The pattern where it gives you the place to bolt it down, plus the 5-bolt pattern for the wheel. Substantial bearings. It's a nice forged piece of steel. And, pretty decent axle. Got a hub, a pilot on the hub that you can center your stuff with. And it costs less than 2 ball bearings to have all that housing and stuff with it. So that looked like a good deal. We'll just turn it around here a little bit. As I went to the trouble of finding it. But the axle is not drawn. I don't think I ever had to change these blades from the shape they are in the prototype here. And the boosters, I went through different iterations of them, more or less of them. In this, the 5 blades seem to be a minimum materials to capture maximum width of the wind. You can see this is the width of the turbine, and this is the amount of air that's going through it. Oh, why does the booster work? Let's talk about boosters here. Go back to the other sheet. That's showing the size of it compared to that center part of the roof. It's in the other videos. This is the roof that sits on top of the spider beam. So the spider beam would be 6 inches less all the way around than this roof, and that sitting in the middle of the whole works. But I erased made a copy of it and erased everything away except the turbine. So if this area here is 1.5 times, well, actually it'd be you're comparing from the intersect from here to there. That's the area the air has to go out through. Is how it leaves the system. But coming in, it has to cover this much. So we went from this width to this width. And that's about 4.5 to 1. So if we had a 6-mile-an-hour wind, which is really light for our site, if we had a 6-mile-an-hour wind, it would be 20 to 22 miles an hour when it went into the turbine, with no mechanical means other than the fact that it has to go between these vanes. This is the same deal that we're using to cool the house with, and it works very well. It's plenty cool in there anytime. We can't get there right now because we're under quarantine, and we're sitting here sweating in town. But out there, when we're out there, especially if you're on the second level where all the fan housing and openings are, but it's cool downstairs because the whole thing is sheltered by the overhangs of the concrete and the shape of the building. So it's a self-shading building, and then we have all this heat removal of air. A lot of air raise a little bit of temperature, takes away a fair amount of heat. Or you can have a little bit of air and raise it a whole lot of degrees temperature and take away heat. But we're not having to really heat the air much because there's so much of it going through there. So when you're standing in that airflow, it doesn't feel hot. It just works well. There's one of those, let's try that, because we can do anything we want over here as long as it's structurally sound and nobody will say anything. If you don't tell them what it does or what it is, not many people are going to figure it out. Anyway, this is our turbine. I don't know how many kilowatts it is, but I look at these ones that are horizontal axis of a similar diameter. The only air that a horizontal axis turbine intercepts is what hits the blades. So if you look up there and you see 80% daylight right through the blade, look at it when it's sitting still, like we're looking at this one sitting still. You're not capturing any energy from that area between the blades. You're only capturing what runs across the blades. That's the only thing that can make lift on the blade. So I don't know how big a horizontal axis would have to be to equal the output of this one, because we intercept not only 100% of the air at the turbine, we're intercepting more air than the disc of the turbine, because the outside of the panels is wider than the turbine. So we're boosting the air that goes through it, and we're boosting the speed of the air, and the power goes up by, best I can tell, about the square of the speed of the air. So it ought to be seriously efficient. And the size, I think it's going to make way too much electric. We can build it, put the stator on it the way I think it ought to be, run it, and if we're getting way too much RPM and too much amps, we can change the wire size and the number of turns on the stator coils to a lot more turns, and we could boost it up to 250 volts right off of the turbine. And then all it takes is a really simple rectifier to, which you're going to have anyway. You have to have that. It turns the AC to DC, and then you can run it across something to make it back into AC. But we could theoretically we could have enough of the phases connected. They run these things as more than 3-phase motors. It has to be multipliable by 3. You can have a 9-phase, a 12-phase, just by how many coils you got and how you can combine them, or it comes out to an equal number of coils in all the phases. We're going with a simple 3-phase. We're not world experts on 3-phase motors, but I do understand how they work and how you commutate them, and got a fair idea of what size wire. Like how I'm going to use 18 gauge wire on this. I'm not sure about the turns. I think I'm going to try to put them in there with one winding right touching the other one, and every two just slap some epoxy on them, so that when I take them off the winder, they won't change. It's like winding slot car motors in the 1970s. We took a 2 or 2.5 volt motor. Well, actually, you take a 12 volt motor and you wind it to 2.5 volts. And the one you could buy them made by Globe, they were 27,000 RPM. They're an instrument, aircraft instrument motor. I don't know what it does. It got to do with gyroscopes though, and they sold just the loose motors, not aircraft certified. They were still, when you could buy a $3 slot car motor for a 1/24th scale, these things was $27. They were 6 or 7 times the price of a motor that was twice as big. But the acceleration ramp on them was really good. They went from a standing start to that kind of RPM in just a few feet. And then the car would straighten out and right off the end of the track. Okay, that's our wind turbine. We've not built it yet. It's not scheduled to be built this year. We want to get the plumbing hooked up and some other stuff. And I guess we'll live in the dark for a while. They may give me electric when we have it totally wired, and I may not even bother asking them. I might go right to initially 12 solar panels, some Chinese solar panels. That'll get me into storage batteries of some kind, and an inverter and all that kind of stuff up and running. And then to make massive power, I can be making this, in the evening, something to do, hobby. But we've settled in on this design. We're not going to change the design. We're happy with every part of it. Okay, and another way too long video. That's probably going to be the biggest detriment to this channel. Of course, nobody watches it, so it's not really that big of a thing. I got up to 9 views on a video this week. I don't know how old it is. Maybe it's a month old, but it got to 9 views. Still no comments on it. I think I have 3 comments on the entire channel from one end to the other. It's interesting. I don't have too many failures. Most everything I do works. The place I worked at was the only criteria on design. They give me a list of specs. I have to meet all of them. I exceed them every time, and knew I was going to. If if they wanted something that had to be make 70, I made sure it made 90. You know, everything was, you know, 20% over. Any kind of materials I want to use, within reason. And we got along. But the only thing is it had to work. They told me if it didn't work, I had to pay for it. So we built these machines anywhere from $16,000, $17,000 to lumber sorters that were over $500,000. And I just had to guarantee it would work. So I enjoyed that part of the job. Not so much the heat and the dirt and everything, but it's all right. Anyway, I got a track record on things working, so I'm not really too concerned that whether or not this will work the way I expect it to. There's been a reasonable amount of research into what I wanted, rather than just sit down and draw. That looks good to me. There's actual some calculations behind this. It's like the floors, the suspended slabs in the house. They're all calculated. 150% load factor on over designed rebar in the first place, and then live load 50 pounds per square foot, and then another safety factor on top of that. So it's typhoon proof and resistant to most everything. Anyway, this is way too long. If you learned anything, not too much from this one, but if you did learn something, you can give a thumbs up and thumbs down, whatever you like. We're not a monetary channel, won't hurt us, won't help us. But if you want to, you go ahead. If you want to comment, I haven't figured out how to separate out comments on the videos so I can read them. I know if I try to play the video, the comments come up and then I can see them. But you know, there's got to be a better way than that, because that way, if I check those things once a week, I'd be putting more plays on the videos than the rest of the world combined. Can't do that. There's got to be a way to do this. I'll have to check into that at YouTube, see what they have to say. I'm sure that there's a way that you can pull up comments you haven't answered. I think I've seen something like that on their analysis thing. Okay, y'all have a great day. Bye.